Good morning, everyone. This is lecture number 17 of the engineering mechanics. During the last lecture, we were discussing about the equilibrium. Then we have seen the conditions for the equilibrium. And then we were discussing about the types of support, corresponding reactions, and the types of load. So we will revise those concepts and then we will start with the problems on the equilibrium of the beams. So in the equilibrium, we have already seen the different types of supports and corresponding reactions. So there are three types of supports. The first support, it is the hinge support. Then second support, it is the roller support. And third support, it is the fixed support. And each support, that is hinge, roller, or the fixed support, it carries different reactions. Okay. So we will see this one by one. So this is just a revision of the last lecture. So the first support, you can see here. So this is the real-time support. So it is the roller support. So roller support, it offers only one reaction and it is represented as so suppose this is one object and it is supported by using the roller support. Then this is the representation. Or we can show the same support like this. If this is one rod or it is a beam, then we can represent the roller support like this. Okay. So both these are roller support. So when we draw the free body diagram, so FBD, so this is the object. And then for this roller support, we have to just show one reaction which is perpendicular to this surface. So this is the direction of this reaction. Suppose this reaction is RA, then in the FBD, we have to just show the reaction RA, which is perpendicular to this surface, not to the object. Okay. Then in the second diagram, suppose this is the rod and this point is A. Then at this point, there will be one reaction which is offered by this roller support. And this reaction RA, it is perpendicular to this surface. Okay, so this is the surface on which roller is placed. And on this roller, we can place any object which is to be supported. Okay, so this is the reaction RA. So this is the representation when we solve the problems on the roller support. So practical application, you can see here. So this is the bridge. So this bridge, it is supported on these two rollers. Okay, so this total reaction, it is perpendicular like this to this surface. So what are the limitations for the roller support? So roller support, it offers only one reaction. So if this is the roller support, so it will offer the reaction in the perpendicular direction to the surface, but it will allow the free movement maybe in the horizontal direction or in the vertical direction. Okay, so this is the limitation of the roller support. So roller support, it can apply the reaction only in the one direction. Suppose we have one system and roller, it is mounted in the vertical direction like this. And there is one object which is supported or it is constrained only in the vertical direction. So it will allow the free movement in this direction, that is a vertical direction, and it will offer the reaction in the horizontal direction, which is perpendicular to this surface. So in the FBD, we have to just draw the rod, and then we will show the reaction in the horizontal direction. So this is the reaction RA. Suppose this point is A. Okay. So this is the roller support, and this is the practical application. So roller support, sometimes they are used to support the heavy load. Here you can see the example of the bridge. Then second support, it is the hinge support. It is also called as pin support or a pin joint. So hinge support, it allows the rotation. Suppose this is the rod. This rod is AB, and it is connected at this point with the help of hinge support or a hinge joint. Then this hinge joint, it cannot restrict the rotation of the rod AB. But if you try to pull this rod from this joint, then we cannot pull this rod. Or if you try to pull the rod in the downward direction from the point A, so we cannot pull the rod in the downward direction. So it will offer the two reactions, one in the horizontal direction and second in the vertical direction. So when you draw the free body diagram for this rod AB, then we have to show two reactions at point A. So this is the rod AB. So one reaction at this point, it is in the vertical direction. So it is VA. And second reaction offered by this hinge joint in the horizontal direction, it is HA. Now the direction of VA and HA, whether it is on the positive Y direction and positive X direction, it depends on the direction of the external force acting on this rod. So for time being, consider we are applying the force on the rod AB in the negative X direction. Suppose this force is 50 Newton. Then in order to balance this 50 Newton, hinge support, it will offer opposite force, that is called as a reaction HA. So for this case, HA, it must be equal to the 50 Newton. So that system or this rod AB, it will be in the equilibrium condition. Okay. And suppose we apply one force in the downward direction. Let us take this force as a 100 Newton. So hinge support A, it will offer the reaction in the opposite direction to the applied force. So this reaction VA, it must be equal to 100 Newton in the upward direction. Okay. So that the conditions of equilibrium, summation Fx0 and summation Fy0 will be satisfied. Okay. So this is the hinge joint, and this is the representation of the hinge joint, and this is the free body diagram. So hinge joint, it has two reactions. One is VA and second is the HA. And this is the practical application. So hinge joint, you can see in case of excavator arm. So this is the excavator, and this is the hydraulic cylinder link. So this cylinder, actually this is a piston. It is connected with the help of hinge joint. So this is the hinge joint. So it can allow the rotation about this point. Okay. But we cannot remove this link, okay, from this part. So it will offer two reactions. So this is the first reaction, which is vertical reaction, and second reaction, it will be the horizontal reaction. So this is the HA. Okay, so this is the practical application of the hinge joint. And the third joint or the support, it is the fixed support. So fixed support, it will offer three reactions. So this is the fixed support. So fixed support, it restrict the rotation. So we cannot rotate the system, and therefore it will offer the moment which is called as a counter moment or the balancing moment. So this is the MA, and there will be two reactions. So one is vertical reaction VA. It is similar to the hinge support, and second will be the horizontal reaction HA. Okay. So HA and VA, they are similar to the hinge support, but there is additional moment which is called as a balancing moment or the counter moment, and therefore fixed support, it offers three reactions. So when you draw the free body diagram, suppose this beam AB, it is fixed in the wall. Then at point A, this is called as a fixed support. So there will be VA, then HA, and this is the balancing moment, which is the MA. So these are three reactions for the fixed support. Okay. So you can see here example. So this is the I beam, which is used for the building construction. Okay. So this I beam, it is connected to this wall. So this is the fixed support. Therefore, if we try to rotate this I beam, maybe in the clockwise or anti-clockwise direction, we cannot rotate this beam. Even if we try to pull this beam in the horizontal direction or in the vertical direction, okay, it is not possible to pull the beam in the horizontal or vertical direction. Okay, and therefore at this point, one reaction will be vertical, which is the VA. Second reaction will be horizontal along this direction, that is the direction of this beam. So this is the HA, and there will be a balancing moment. This is the balancing moment, which is the MA. Okay. So such type of support, it is called as a fixed support. So I hope this point is clear. What are the types of support and corresponding reactions? Then the second part that we were discussing in the last lecture, it is the types of load. So in the types of load, the first load, it is the point load. So point load means what? The load is concentrated only at single point. So suppose this is one object and we are applying some force. Suppose force value is F is equal to 20 Newton and it is acting at this point A. So 20 Newton, it is concentrated exactly at point A. Suppose we try to pull this object by connecting one cable. So this is the cable, okay? And we are applying a force that is called as a tension force of 100 Newton. So this tension force of 100 Newton, it will pass through this cable and it will act on this object at this point. So tension 100 Newton is concentrated at the point B. So this is called as a point load. Then second load, it is the distributed load. So in the distributed load, the first type, it is the UDL. So UDL, it is called as a uniformly distributed load. Okay. So uniformly distributed load means what? It is equivalent concept for the pressure force. So when we take the pressure, it is the distribution of force on some area. So suppose this is the area. This is a rectangle. and this is the force which is acting on this area. Okay. Suppose this area is 1 by 1, that is 1 meter by 1 meter. Okay. And force, suppose it is 100 Newton. When 100 Newton force it is distributed on this area 1 by 1, then we can find out the pressure which is equal to force per unit area. Okay. So unit area means what? It is 1 meter by 1 meter. So it will be 1 meter square. So force is 100 Newton. Area is 1. So in this case, we can say 100 Newton per meter square. Okay. So this pressure P, its unit is Newton per meter square. It shows the distribution of force on the unit area. Okay. So this is the two-dimensional analysis. That is the pressure. Okay. Now suppose we want to show the distribution of force on a single line, then we have to consider the UDL. Okay. So what is UDL? Suppose this is the beam. You can consider this is the I beam. Okay. And it is supported with the help of a pillar, or we can say it is a column. Okay. So this beam AB. So this is the column at point A. This is the column at point B. And there is a load of the ceiling, or we can say it is a cement concrete. Okay. So this cement concrete loading, it is shown with the help of UDL. So this UDL is nothing but the force distribution on the beam AB. And for this UDL, the intensity, it is represented by the W. Okay. So this W, it is similar to the pressure. So only difference is pressure, it is used for the force distribution on the area, and the UDL, it is the force distribution on the single line. So W is given as, suppose the value is 100 Newton per meter. So this is the intensity of the UDL. So 100 Newton meter, it is distributed over this beam AB. Now when you draw the free body diagram, then in the free body diagram, just draw the beam AB. Then convert this UDL, which is intensity is 100 Newton per meter, into a single point, which is called as a point load. So this point load, it will act exactly at the center of this beam AB. Suppose the beam AB, its length is 5 meter. So the point load F, which is because of the UDL, it is given by intensity into this span L. So span means distance between AB. So intensity is 100 Newton per meter into length, which is equal to 5 meter. So meter, we can cancel out. So remaining value is 100 into 5, that is 500, and unit is Newton. So this is the point load because of the UDL. So this is the conversion of the UDL into point load. And this point load, it will act exactly at the center. So this is 2.5 and this will be 2.5. Okay. Then second loading, it is the UVL. So it is called as uniformly varying load. So uniformly varying load, the intensity, it is continuously increasing in the linear manner from one point to the other point of the system. So suppose this is the beam AB and this is the support reaction. Suppose this reaction is RA and this is the RB. And there is a UVL. So this is the representation of the UVL. So basically it is a force distribution. So only difference is this force distribution, it is varying in the linear manner from one point to the other point. So at point A, the intensity is 0. And this is the maximum intensity. So it is represented as W. Suppose this intensity, it is 50 Newton per meter. And the span of this complete beam, it is 5 meters. Then when we draw the free body diagram, we have to convert that UVL into a point load. So for the conversion, point load F, it is equal to 1 by 2 into this maximum intensity W into this span, which is L. So basically this is the formula of the area of triangle, 1 by 2 height into base. Okay. So it is equal to 1 by 2, W is 50 and L is 5. Okay. So this is equal to 125 Newton. So W is Newton per meter and this is the meter. So remaining unit is 125 Newton. So this is the point load. Now application of this point load. So it will act at this point and distance with respect to this 90°, it is equal to L by 3. And with respect to the other point, it is 2 L by 3. So in the FBD, we have to just show the point load because of the UVL. So this is the F. So for our example, it is 125 Newton. With respect to this point, that is the point B, or we can say it is a 90° angle for that UVL. It is equal to L by 3. So this is 5 by 3. And with respect to the other side, it is equal to 2 L by 3. So it is 2 into 5 by 3. So this is 10 by 3. So this is the free body diagram for this beam AB. And if there are supports, then these are the support reactions RA. And this will be the support reaction RB. Okay, so this is the conversion of the UVL into a point load. Okay, so I hope this point is clear. What is a UDL and what is a UVL and how to convert UDL and UVL into point load. So the problem statement is find the support reactions at point A and point B, where A is the hinge support and B, it is the roller support. So basically, this AB, it is the beam AB. So beam is the structural member which is used to support different loads. So on the beam AB, there are different loads acting. The first load, it is 25 Newton. So this is the point load. Then second load, this is the UVL, which is called as uniformly varying load. Okay. So this UVL, it has maximum intensity. So this is the W. It is equal to 10 kilonewton per meter. And its span, it is equal to 4 meter. That means from point A to C. So this is the point C. Then at point F, there is another point load of 30 kilonewton. It is acting at 40 degree with respect to the horizontal. And this part DEF, it is the extended portion of the beam AB. So it is the part of AB. So we have to find out the reactions at point A and reactions at point B. So this point A, it is the hinge support. And the point B, it is the roller support. So the first step, when we solve the problems on the equilibrium, draw the free body diagram. Okay. So free body diagram means what? Isolate this beam AB from its supports. So there is support at point A, which is a hinge support, and support at point B, which is the roller support. So just draw the diagram for this beam AB. Then show the reactions at point A and reactions at point B. And then show the different forces acting on that beam AB. So here you can see, draw the beam AB as it is. So this is the DEF, which is the extended portion. Then next step is at point A, there will be two reactions. One is VA, and second reaction, which is the horizontal reaction, that is the HA, because this is the hinge support. Then at point B, there will be one reaction which is perpendicular to this support or to this surface. So this reaction, it is the RB. So show this reaction as it is at point B. This is the RB. Then show the forces 30 kilonewton and this 25 kilonewton as it is at point C and at point F, because these are the point load. Okay. So this is the 25, and at point F, this is the 30 kilonewton. This angle is 40 degree. Then there is a UVL whose magnitude is 10 kilonewton per meter. So for the UVL, when you draw the free body diagram, convert that UVL into point load. So for the conversion, we have the formula. So conversion is F is equal to 1 by 2. This intensity, that is nothing but the height, which is 10, into base, which is called as a span, which is equal to 4. So it is equal to, this is 40 divided by 2. So it is 20 kilonewton. So this is the point load because of the UVL. And this is the point or point of application for this point load. And this distance with respect to this 90 degree, it is equal to L by 3. So right now L is 4 meters. So this is 4 by 3. So you can see here. So this is the 25. This is the point load, and this load, it is nothing but the F, which is the point load because of this UVL. It is equal to 20. Then this span or distance, it is equal to 4 upon 3. Then this is 30 kilonewton acting at 40 degree. Then there is a reaction RB, and this is VA, and this is HA. So this is the complete free body diagram for the given beam AB. Okay. So after this free body diagram, next step is we have to find out these reactions. That is value of VA, HA, and the value of the RB. So to find out these reactions, HA, VA, and RB, we have to use the conditions of equilibrium. So in the FBD, there are three unknowns. One is HA, VA, and reaction RB. So we have to use the three equations or three conditions of the equilibrium. So first condition is summation Fx, it is equal to 0. Then summation Fy, it is equal to 0. And summation of moment about any point of that system, it must be equal to 0. So by using these three conditions, we can find out these three unknowns. So to apply this equation, just refer the free body diagram. So I will redraw that free body diagram. So this is beam AB. At point A, there are two reactions, VA, second reaction is HA. Then reaction RB at point B. Then there is an extended portion. And this is the point load of 30 kilonewton acting at 40 degree. This is the point load, 25 kilonewton. This is point C, and there is a point load because of the UVL, which is F is equal to 20 kilonewton. It is acting at 4/3 with respect to point C. This total distance A to C is 4 meter. Then this is 2 meter. Okay, so this is complete free body diagram. Now refer this equation, summation Fx0, summation Fy0, and summation of moment 0. So if you apply the third equation, summation moment 0, then we can find out one unknown, that is the reaction RB. So when you use summation of moment 0, you can use that summation moment 0 at any point of that system. You can apply it for A, C, B. But how to decide the correct point so that we can find out at least one unknown out of these three unknowns? So select the point for moment where maximum unknown will meet. So if you select the point A, then there are two unknowns, VA and HA. Okay. So we can cancel out the moment of VA and HA by taking the moment about the point A. And therefore, select A as a moment point. So I will write the equation summation of moment at point A by all the forces, it is equal to 0. So this is the third condition. So now take the moment by all the forces about the point A. So first is the reaction RB, which is unknown and which is to be determined. So what is the moment of reaction RB about the point A? So reaction RB into its perpendicular distance with respect to point A. So it is 4 plus 2 plus 4. So that is 10 meter. So RB into 10. Now this moment, it will try to rotate the beam AB in the anti-clockwise direction. So it is positive. Then second moment, it is because of this 30 kilonewton. But for 30 kilonewton, direct perpendicular distance is not available. So we have to resolve that force. So this is the X component, which is equal to 30 cos 40. And this is the Y component, which is 30 sin 40. And now take the moment by this 30 cos 40 and 30 sin 40. So first select 30 cos 40. So what is the perpendicular distance for 30 cos 40? So this is the perpendicular distance with respect to point A. Because if you extend this line of action, so this will be the perpendicular distance for 30 cos 40. Okay. And this is equal to this length. And that is equal to 1.5 meter. So this is given as 1.5 meter in the problem. So perpendicular distance is 1.5 meter and this is the force. So moment will be 30 cos 40 into distance is 1.5. And the sense of rotation, again, it is clockwise. So it will try to rotate the system in this direction. So this moment is also positive. Then consider 30 sin 40. So for 30 sin 40, the perpendicular distance so this is the line of action. So this total distance from this point up to the point A, it is nothing but the perpendicular distance. So it is 6 plus this distance. So that distance, it is equal to 2 meter. So this is given as 2 meter. So 2 plus 2, 4 and 4, 8. So moment is 30 sin 40 into 8 meter. And this moment, it is in the clockwise direction because this force, it will try to rotate the system, that is a beam AB, in this direction. So it is negative. The next moment, it is because of 25 kilonewton. So force is 25 into distance is 4 meter. And again, this moment, it is clockwise. So this is minus. Next is 20 into perpendicular distances. This is 4 and this is 4 by 3. So it is 4 minus 4 by 3. And again, this moment is clockwise. So this is minus. And moment by this HA and VA about point A, it is 0. Because these two forces or two reactions, they are passing through the point A. So there is no perpendicular distance and therefore moment is 0. So equate this complete equation to 0, and then in this equation there is only one unknown, which is the reaction RB. So we can find out the reaction RB. So if you solve this complete equation, then you will get the reaction RB, which is equal to 27.31 kilonewton. Okay. So you can check the answer. Reaction RB is 27.31. So once we get reaction RB, then you can use the remaining two equations, summation fx0 and summation fy0. So first use summation fx0. So for summation fx0, consider the x components. So first is HA, and it is acting in the positive x direction. So we have considered HA as a positive x direction. Even you can consider it is in the negative direction. So other force in the x direction, it is 30 cos 40, and it is in the negative x direction. So it is minus 30 cos 40, which is equal to 0. So HA reaction, it is equal to directly 30 cos 40, which is equal to 22.98, and unit is kilonewton. So as we have considered HA reaction to be acting in the positive x direction, and our answer is positive, that means our assumed direction is correct. Okay. Suppose we select the HA on the negative side like this. Then in the summation fx, we have to take this HA value as a minus. So HA value in the calculation, it will become minus 30 cos 40. So as HA answer is negative and our assumed direction to be on the negative side, okay, so correct direction, it must be on the positive side. So our first assumed direction, it is on the positive side and answer is positive. That means our assumed direction is correct. And to find out the VA reaction, consider the summation F1. So take summation Fy is equal to 0. So for summation Fy, first is VA acting in the positive y direction. Then 20, 25, they are in the negative y direction. So it is minus 20. Then minus 25. Then next is minus 30 sine 40. And then plus this reaction RB. It is equal to 0. So in this equation, RB reaction, it is already calculated, which is 27.31. So this value is plus 27.31. Okay, so now solve this equation and find out the VA. So VA reaction is 36.97. And answer is positive. That means our assumed direction is correct. VA, it is acting in the upward direction. Okay. So these are your final answers. Reaction RB, reaction at point B, HA and VA, these are the reactions at this hinge point. Okay, so I hope this procedure is clear. How to solve the problem and how to find out the support reactions. Okay, this is the second problem on the equilibrium of the beams. So in this problem, so this is the fixed support. So you can take this point as A. So this is the vertical wall, and this beam AB, it is connected to this wall. So basically it is fixed to the wall. So at point B, there is a roller support. And this roller support, it is mounted on the inclined surface. So this inclined surface, it has an inclination with respect to horizontal of 30 degree. And this beam AB, it is loaded with the help of UDL and the point load. So this is the UDL. So this is point C. This span is 2 meters. This intensity for this UDL, which is W, it is equal to 10 Newton per meter. There is one point load at point C, which is F is equal to 20 Newton. It is acting at 30 degree. So the question is, we have to find out the support reactions. At fixed point A and point B. So point B, it is the roller support, and A point, it is the fixed support. So the first step is we have to draw the free body diagram. So this part, it is the UDL. So UDL, it can be represented like this. So suppose this is the beam AB, or it can be represented like this. So meaning is same, both are UDL. So first step, when you solve the problem, you have to draw the free body diagram. So for the free body diagram, just isolate this beam. So this is the beam AB. So point A, it is the fixed support, and point B, it is the roller support. So for the roller support, there will be one reaction, and that reaction, it will be perpendicular to this surface on which roller is mounted. So this is the reaction. It is perpendicular to this inclined surface. So this is the reaction RB. So this angle of the reaction RB, you can find out by using this geometry. This is 30 degree, this is 90. So this angle will be 60 degree. Then at point A, as this is fixed support, there will be three reactions. One is vertical reaction, which is VA. Second will be the horizontal reaction, that is HA. You can see in the original diagram. So this is vertical reaction, this is horizontal reaction, and there will be one moment. This is the balancing moment, which is MA. So you can show that moment on the free body diagram. Okay. Then next, show the forces 20 Newton as it is. So this is the point C. The angle of 20 Newton with respect to x-axis, it is 30 degree. And then convert this UDL into point load. So how to convert UDL into point load? Point load value F, it is equal to W into L. So W is 10 Newton per meter, and length, that is a span, which is equal to 2 meter. So this is the point load because of this UDL. So show this point load exactly at the center. So BC, so this is C point, it's 2 meter. So this is 1 meter and this will be 1 meter. And this F is equal to W into L, that is 20 Newton. So this is the point load because of the UDL. Okay. So this is complete free body diagram for the given fixed beam AB. Okay. Now next part is we have to find out the RB, HA and VA. So as there are three unknowns, we have to use three conditions. One is summation Fx0, then summation Fy0, and third condition, it is summation of moment 0. Okay. So now you can use summation Fx0, summation Fy0, and summation of moment 0. So first, use the summation of moment 0 and find out this reaction RB. So you can take the moment about the point where there will be maximum unknowns. So at point A, this is the hinge joint. So there are two unknowns, HA and VA. So take the moment point as a A. So summation of moment at point A by all the forces, it is equal to 0. Okay. Now by applying this condition, you can find out this reaction RB. Okay. And then use summation of Fx0 and summation of Fy0. So by using first condition, you will get the reaction RB. From summation Fx0, you can find out the HA, and summation Fy0. You will get the VA reaction. Okay. So try to solve this problem as a homework. So we will stop here. So just give your attendance in the chat box.